In this video, I will discuss the operation of a Schmitt trigger circuit. After discussing the theory, I will show you a multisim simulation of the Schmitt trigger circuit to verify my circuit analysis. So what is a Schmitt trigger circuit? The Schmitt trigger circuit is a comparator circuit which will rapidly changes its output voltage when input voltage arrives at the upper or lower threshold level. The Schmitt trigger circuit is a comparator circuit, and if you are familiar with the comparator circuit, in any comparator circuit we will apply an input voltage, and the input voltage will be compared with a reference voltage, and in the Schmitt trigger circuit, depending upon the output voltage, it will set two reference point, upper triggering point and lower threshold point. When the input voltage arrives at either upper threshold or lower threshold point, the output voltage will change its position from one level to another. Thus it will produce a square waveform in the output terminal. Therefore the Schmitt trigger circuit is often termed as squaring or squarer circuit. So this is our Schmitt trigger circuit, consists of transistor. This Schmitt trigger circuit will use two identical transistors, Q1 and Q2, and in this circuit we will have total 7 resistors. The base bias resistor of the transistor Q1 is RB1 and the collector load resistor is RL1. The collector load resistor of the transistor Q2 is RL2, and you will see that the emitter of the transistor Q1 and the transistor Q2 are connected at the same point, and that point is connected at one end of the emitter bias resistor RE, and another end of this RE is connected with the ground. And you will see that the collector of the transistor Q1 is connected with the base of the transistor Q2 through this R1 resistor, and the one end of this R2 is connected with the base of the transistor Q2, and another end of this R2 is connected at the ground. Now let me describe the operation of this Schmitt trigger circuit. How this Schmitt trigger circuit acts as a comparator circuit and generates a square waveform. Initially, let's say our applied input voltage is 0. We are powering this Schmitt trigger circuit with this applied input, with this bias voltage plus VCC, and at the input side we are applying a sinusoidal input voltage Vi. Initially, let's say this input voltage is equal to 0. That means this end of this RB is directly grounded, or this could be an open circuit. As the input voltage is equal to 0, that means as the input voltage is less than the 0.7 volt, therefore this base to emitter junction will not be in forward bias. Our transistor Q1 will be in off state. So when the transistor Q1 is in off state, now I can disconnect the collector and emitter terminal from our original circuit. If I disconnect the transistor Q1 from the circuit, you will see that this plus VCC will be applied between this point, and another way of this and this plus VCC will be applied between this point and this ground, and you see that some portion of this applied plus VCC will be dropped across this RL1, across this R1, and across this R2. The portion of this plus VCC that is dropped across this R2 will be our VB2, and that this VB2 will be used to bias the base emitter junction of this transistor Q2, and this RL1, R1 and R2 will form a voltage divider circuit. As the resistor RL1, R1 and R2 are connected in series, and therefore I can form a voltage divider circuit like this, and at one end of the RL1 we are applying our plus VCC. The voltage that is dropped between the C terminal and the ground is our VB2. We can calculate VB2 by using our voltage divider rule. I want to calculate the voltage drop across this resistor, therefore I will take the value of this resistor in the numerator, and in the denominator I will add the three resistors of RL1 plus R1 and R2, and multiply this fraction with the total voltage plus VCC, and this is our VB2. As the current will enter from this direction, therefore this terminal of this R2 will be positive and this terminal will be negative. So this end of this VB2 will be positive and this end will be negative, and you will see that, and this VB2 will be sufficient to drive this transistor Q2 in saturation region or in on state. So when this transistor Q2 is in on state, that means this collector and emitter terminal will get shorted. When this transistor is in saturation region, therefore, or in on state, therefore a saturation current IC2 will flow in the collector terminal of this transistor Q2, and the same IC2 will flow through this RL2. Therefore I will get a voltage drop IC2 across this collector load RL2, and from that means from this point to this point we will have a voltage drop IC2 RL2. Now we are taking the output across this terminal and this terminal, therefore our V out will be equal to, see here we are applying plus VCC, and a portion of this plus VCC gets absorbed across this load resistor. Therefore the remaining of this plus VCC will be equal to our output VCC minus IC2 RL2 will be our output voltage. So when this transistor is in on state, we know that the emitter current of a transistor IE equal to the sum of the base current plus collector current, and if I consider this base current is negligible, therefore our IE emitter current will be equal to collector current. Therefore I can consider this IC2 will flow through this emitter terminal, that means IC2 will be equal to our IE2, and this IE2 will flow through this emitter bias resistor RE. Therefore I will get a voltage drop VE across this resistor. This terminal will be positive and this terminal will be negative as the current is entering from this direction, and I will denote that voltage with VE, and the value of this VE will be equal to IE2, as the IE2 and IC2 are equal. Therefore I will write it like this, IC2 RE, and you will see that the positive end of this VE is connected with the N-type emitter of the transistor Q1. That means negative terminal of this VE is connected with the P-type emitter. That means this VE will put the base to emitter junction of the transistor Q1 in more reverse bias. That means if I want to turn on the transistor Q1 in normal mode, we have to apply a voltage greater than this base to emitter junction voltage, but here we have additional voltage VE, which is also responsible to keep the base to emitter junction in reverse bias. Therefore we have to apply a voltage VE1. In addition to, we have to apply another voltage VE to turn on the transistor Q1, and this will set a reference level in this circuit, and we call that point as upper triggering point, and this voltage VBE1 plus VE is known as upper threshold voltage. So when we supply this total circuit with this plus VCC volt, it will set a reference point upper threshold voltage or UTP, upper triggering point, equal to VBE1 plus VE. That means to turn on the transistor Q1, we have to apply a voltage between the base terminal of the transistor Q1 and the ground terminal greater than the UTP. When the input voltage Vi is greater than UTP, then our base to emitter junction of the transistor Q1 will be in forward bias. Therefore transistor Q1 will be in on state. Now let's say I am applying a sinusoidally varying voltage between the base terminal of the transistor Q1 to ground terminal. As we are applying a sinusoidally varying quantity, that means from 0 to after certain time it will come to positive maximum, after that it will return to 0, after that it will go into negative maximum, after that it will again come to 0 volt. So when this applied input voltage is greater than our upper triggering point, it will turn the transistor Q1 on by keeping the base to emitter junction of the transistor Q1 in forward bias. When the transistor Q1 is in on state, that means I can short the collector and emitter terminal of the transistor Q1. When the transistor Q1 gets shorted, therefore I will get a saturation current in the collector terminal IC1 of this transistor Q1. Previously, when the transistor Q1 was in off state, that means there was no collector current. If I consider the current through this RL1 equal to IL1, our IL1 was equal to I2, but now we have an additional current IC1, and this IC1 is the saturation current of the transistor Q1. Sudden flow of this IC1 will increase the value of this IL1 drastically, and you will see that as the value of this IL1 increased, therefore the value of IL1 RL1, that means this ohmic drop, voltage drop, will also increase. And I have shown you that this RL1, R1 and R2 form a voltage divider bias circuit in which this entire VCC gets absorbed. Now, as the value of the voltage drop across this terminal and this terminal, that means across this RL1, is increased drastically, therefore the voltage difference between this point and this point will be reduced. That means the voltage difference between this point, this C terminal, to ground will also decrease. That means now the voltage difference, as the voltage difference between this point and this point is reduced, therefore it will not get sufficient voltage to drive the base to emitter junction of the transistor Q2 in on state. Therefore our transistor Q2 will be in off state, and when the transistor Q2 is in off state, I can disconnect the collector and emitter terminal of the transistor Q2, and you will see that the collector current IC2 will be equal to 0. Therefore IC2 RL2 will also be equal to 0. That means now our output voltage will be equal to plus VCC. This applied VCC will be appeared across this terminal and this ground terminal, because there is no other voltage absorbing element. Now consider the emitter current of the transistor Q1. We know that the emitter current of a transistor IE equal to the sum of the base current and collector current. The base current is negligible in terms of this collector current, therefore I can neglect the base current. Therefore our IB will be equal to IC. See, if I consider the IE equal to IC, therefore IE1 or the emitter current of this transistor will be equal to IC1, and you will see that as there is no incoming current from this direction, therefore this IE1 or IC1 will flow through this RE, and it will create a voltage drop across RE resistor IC1 RE, which I will denote with VE prime. This VE prime will be equal to IC1 RE. See, previously the voltage difference between this end and this end was equal to VE. Due to the on state of the transistor Q1, the voltage difference between this point and this point has changed to VE prime. It will create a new reference label LTP, lower triggering point, equal to VBE1 plus VE prime, and when the input voltage Vi will be less than our LTP or lower triggering point, that means the base to emitter junction voltage of this transistor Q1 will not be sufficient to drive the transistor Q1 in on state. Therefore it will go in off state, and when this transistor gets into off state, the transistor Q1 will now be in on state, and when the transistor in on state, the voltage difference between this collector to ground terminal will be again VCC minus IC to RL2. This is how the alternative switching of the transistor Q1 will Q and Q2 will shift the level of the output voltage from this level to this level, this level to this level, this level to this level, and this process is a very fast process, and the transition from this level to this level or this level to this level is almost instantaneous. Okay, so this is the operation of the transistor Schmitt trigger circuit. Now let me summarize the operation of the Schmitt trigger circuit in 4 lines. Initially our input voltage was equal to 0, therefore transistor Q1 will be in off state. At that time I have supplied the VCC voltage in the Schmitt trigger circuit, which will turn the transistor Q2 in on state. Therefore I will get a collector current IC2, and it will create a voltage drop IC2 RE across the RE resistor, which will create a reference point VBE1 plus VE, and that voltage will be known as our upper upper triggering point. Now I will apply our input voltage Vi in the circuit. When this input voltage will be greater than UTP, our output voltage will be equal to plus VCC. When the input voltage will be greater than UTP, our voltage drop across this RE will now be equal to IC1 RE, which I will denote with VE prime. And as previously the voltage drop across this RE was equal to VE, and when the input voltage crosses this UTP, our voltage drop across this RE will be equal to VE prime. That means now when this input voltage crosses this UTP, there will be a change in the reference level from UTP to LTP, and when the input voltage will cross this LTP, our output voltage will be equal to VCC minus IC to RL2. This, and it will create a voltage drop VE across our RE resistor, and you will see that there will be a shift again in the triggering point of the transistor. Okay, so when the input voltage will be greater than UTP, our output voltage will be VCC, and when this input voltage crosses the UTP level, our reference level will have a transition UTP to LTP, and when this input voltage will be less than LTP, our output voltage will be equal to VCC minus IC to RL2. And now I will show you this property in the waveform. So this is our applied input voltage. As VE is greater than VE prime, therefore our upper triggering point will be situated above our LTP. And let me start my analysis from this point. When input voltage is greater than our VI is greater than UTP, our output voltage will have a transition from this level to VCC. Our output voltage will be equal to VCC, and our reference point will now shift from UTP to LTP, and as long as our input voltage will be greater than this LTP, our output voltage will stay at this plus VCC level, and you will see that our input voltage is changing like this. At this point, input voltage is crossing the LTP point. So when the input voltage will be less than our LTP, our output voltage will be VCC minus IC to RL2. See, our output voltage will now have a transition from this VCC to this VCC minus IC to RL2. As the input voltage is less than LTP, there will be again a transition from in the reference level from LTP to UTP. As long as the input voltage is less than this UTP, our output voltage will situated at this level VCC minus IC to RL2, and you will see that at this point our input voltage is crossing this UTP level. When the input voltage will be greater than UTP, our output voltage will again come from this VCC to minus this level to plus VCC level. See, at this point it will have a transition from this level to this level, and our reference level will now again have a shift from UTP to LTP. That means this will be our reference voltage. As long as the input voltage will be greater than this LTP, our output voltage will be at plus VCC, and you will see this that at this point our input voltage is crossing this LTP. When the input voltage is less than the LTP, our output voltage will be equal to VCC minus IC to RL2. That means output voltage will again come from this point to this level, and it will again have a transition in the reference level from LTP to UTP. And when this input voltage is crossing the UTP, we will again have a transition in the output voltage from this level to this level, and this is how it generates a square waveform. Now let me run the simulation to show you the square waveform that is generated from this circuit. Here I have this VCC equal to 5 volt, and from the function generator I am supplying 10 volt peak voltage, sinusoidal peak voltage in the circuit. At first, when this applied input voltage is equal to 0, in that case you will see that as this is 2.2 and 1.1 kilo ohm, and this is a 3.3 kilo ohm resistor, that means 2.5 volt will be dropped between this point, and that will drive the transistor Q2 in forward bias, and you will see that this RE drop will be equal to 1.866. this VE and the built-in potential between this base to emitter junction will form our upper triggering point. Now if I supply the input voltage, you will see that in the oscilloscope I will get a square waveform like this. When the input voltage is greater than the upper triggering point, see here, when the input voltage is greater than the upper triggering point, our output voltage will be at plus VCC level, and when the input voltage will be less than the LTP, our output voltage will be at VCC minus IC2 RL2 level. See here, this level is at 5 volt and this is our VCC, and see here, this is our VCC minus IC2 RL2, which will be 3.755 volt. That means IC2 RL2 was equal to 1.25 volt. And if I zoom this, you will see that this will be a square waveform. Okay, that's it. Thank you.